Okay, good afternoon. Couple of announcements. Homework assignments were posted, and then quiz is tomorrow. Okay, so homework assignments were posted, and the second announcement is quiz is tomorrow. I hope everybody saw that on Canvas, right? And then there will be, so this was mesh current analysis. Next week, there'll be one more homework assignment for Thevenin Norton, and maybe a smaller one after that for source transformation, perhaps. So one assignment for Thevenin Norton and maybe a smaller one after that. But then we are done. Okay. All right. So let's go to our notebook. And you're not studying this until 306 or 307. So let's go up top. 113. All right. Equivalent circuits, example 2. Any questions so far about anything we have done? Okay. All right. Calculators out. And this is a very, well, I said that about the previous one too, but this is an interesting circuit. We have two sources in here. We have a voltage source on the left. You have a current source up top. We are asked to find the Thevenin and Norton equivalent circuits if the 17 ohm was the second circuit or if it was representing the load. And again, terminals of analysis are defined for us. A and B. And I'm going to remove 17 ohm from my analysis. So it's going to look like this. I have a 1.5 amp current source at the top, resistor, output resistor, and then voltage source on the left. And that does it. Okay. This is going to be A. This is going to be B. 17 ohm is not part of the analysis. 5 ohm, 20 ohm, 10 ohm. All right. Oh, current source, 1.5 amps. So find the Thevenin and Norton equivalent circuit as seen from the perspective of the 17 ohm resistor. Always tell students start with the Thevenin resistance first if the circuit seems simple enough. Okay. In this case, if I do start with the Thevenin resistance, first step is to reduce all the independent sources to zero, meaning the 20-volt source is replaced with a short circuit and the current source is replaced with an open circuit. If I do that, then I'm left with 3 resistors, and it is possible to reduce those 3 resistors down to one single Req. Okay. Again, remember that it's not always possible to find Req. In this case, it is possible. So we can begin with RTH. For Thevenin resistance, we modify the original circuit. And when we modify it, all I need to do is copy paste. Oh. All right, let's make this disappear. It's the voltage source, and this becomes an open circuit. Basically, no need to even like draw it. Okay. All right. So 5, 20, and 10. What is REQ? At this point, I would assume that students are able to solve this by themselves. So what is REQ? Anyone? 0.2. Let's see. 5 and 20. So 25, no, not 25, sorry, 100. So 100 divided by 25, so you got 4 plus 10. So the answer here would be, well, not answer, the circuit would be that we start looking here. So this is our EQ as seen from the perspective of A and B. And so at the farthest end, we have 5. It's now connected to the other end of 20. So 5 and 20 are in parallel. And then that brings those resistors in series with a 10 ohm resistor. Answers? 14, 14, 14. All right, so my RTH is 14 ohms. By the way, if you recall, if you have 2 resistors in parallel, like this, then it's the product of the 2 divided by the sum of the 2. So 5 times 20 is 100 divided by 25. 4 is 10, 14. All right, so RTH is 14 ohms. Then again, we forget about this result. Does not have any bearing on VOC or IN, right? Sorry, VTH and IN. Thevenin voltage and Norton current does not depend on the circuit. You have to redraw the circuit again. So let's try Thevenin voltage now. Thevenin voltage, we gotta have the same circuit again. And this time, we keep the terminals open. I'm going to choose a polarity this way, plus minus. Does not really make a difference what you choose. But my Thevenin voltage, VTH, is VOC. So what technique would you choose to solve for VOC? What do you think? There's three primary techniques. You have node voltage analysis, you have mesh current analysis, and you have superposition. How many want to solve it using node voltage? All right, 1. How many with mesh current? 1, 2. How many with superposition? 1, 2, just 1? How many doesn't want to solve it at all? All right, it's going to take long, but why don't we try all 3? So let's say node voltage analysis, right? How many nodes do we see? We see there's a node at the bottom, which is node B. We have node A at the right. We need to find VAB. Let's call this node C. And let's call this node D. If I choose B as my reference, A and B are given as uppercase, and I'm just using that. So let's say choose B as reference. Therefore, VB is equal to 0. And also, VD would be 20 volts. So I am left with two unknowns, VA and VC. So I need at least two equations to solve for this. Okay, VA and VC, two unknowns. And so we need 1, 2, 3, and 4. Yeah. What do you think? 4 nodes, right? Any more or any less? Okay. All right. So VD is 20, VA and VC are unknowns. Let's write KCL. So now for KCL, I need to assign branch currents. And I'm going to have to name this. This is going to make our job easier. Okay. Look at the 4 branch currents. What do you see? The 1.5 amp current source has nowhere else to go except through the 10 ohm resistor. Node A is open. It cannot go anywhere except through the 10 ohm resistor, right? So it's flowing into the node in this direction. But it is also true at the same time that the current going through here is 1.5 amps because it is a 1.5 amp current source. So anything that's in the pathway for the current source, at least up to this node, from this point up to here, must be 1.5 amps. So what do you think is going on with the current source and the 10 ohm resistor? And the answer is there in the arrows, of course. It is just looping around itself. It's not doing anything, it's just looping around itself, which is not quite obvious with the way the circuit is drawn, but because it's an open circuit over there and there's a short over here, learning moment, if you have something like this, that's a closed loop and it's a current source, current's going to keep flowing through there. Nothing else is going to happen. And so I can write ID is equal to IC. And if I'm doing that, that means that the voltage is applied only to the 5 ohm and the 20 ohm resistor. Also, if 1.5 amps is flowing through the 10 ohm resistor, we can find the voltage drop across the 10 ohm resistor, right? 1.5 times 10, so 15 volts. So voltage across 10 ohm resistor, which side is the plus and which side is the minus? Is the plus on the left or is it on the right? So on the right, absolutely. Because current's entering from the right. And so here we have 15 volts. This is A and this is C. But now VAB, node voltage VA would be VAC plus VCB. So let's write an equation. Since we are doing this using node voltage analysis, let's write KCL expression at node C. And I would get ID. Actually, technically, the equation would be ID plus 1.5 equals 1.5 plus IC. Right? Technically, that would be the correct equation. Two currents coming in, two currents going out. But the end result is that ID is equal to IC. ID expressed in terms of the resistor would be 20 minus VC divided by 5. And then IC is VC minus 0 divided by 20. Cross multiply, and I get what is VC? VC is 400 divided by 25, so it's 4. So what, 16? 25 times 4 is 100, times another 4 is 400. Yeah, VC is 16 volts. Let's take a pause while you write it down. Think over that. Let me know if you have any questions. Scroll. The steps make sense? Any questions? And again, I would like to remind students, whether it's node voltage, whether it's mesh current, if you approach it step by step, there is no circuit that you would not be able to solve. Even though the circuit might look, like with 10 different nodes and looks very complicated, if you approach it step by step, it should work out. Okay. All right. So VC is 16 volts. What does it mean for VA? We could still solve it by applying KCL, but we have no need to. Right? We applied KCL at A and we obtained 1.5 is equal to 1.5. VA is VAC plus VCB. The difference in the voltages, we're simply taking the measurement across the two, and therefore V is 15 plus 16 VA is 31 volts. Okay, VA is 31 volts. And its Thevenin resistance is 31 volts. Okay. Every circuit is different, but again, Thevenin and Norton is the setup of the circuit that is the most important. Okay, once you have the setup correct, then you can apply any analysis technique you want. Okay. This also carries over into superposition and mesh current analysis. Because in superposition, what do? We analyze with one source active at a time, right? So if one source is active at a time and you apply superposition, what do we obtain? We want to find VA, right? Let's say only the current source was acting at a time first. So you have the current source. And you have VA. And this is VB. You have a resistor here. And you have another resistor here. The voltage source is replaced with a short. But in any case, it's not going to affect the circuit because VA, due to this 1.5 amp current source, is 1.5 times 10 is equal to 15. And in the second part, where you have the voltage source active, it's 20 volts. A, B, and current source is reduced to 0. You have two resistors, 5 and 20 ohm. It's the same principle. When you have a resistor that is open at one end, both ends of the resistors have the same voltage. So VAB is the voltage across the 20 ohm resistor, because of course this is the same node, right? So A is the same potential as this, because the 10 ohm resistor is open. And so plus minus across the 20 ohm. So VR 20 ohms is 20 times 20 by 20 plus 5. 400 divided by 25, 16 volts. Principle of superposition. VAB is 15 plus 16, 31 volts. Same answer. Let's take a pause. Let me know if you have any questions. Let me know if something doesn't make sense.
Could you explain how you got 15 volts for VA again?
So VA is measured with respect to this node terminal down there. Well, when the current flows, the 1.5 amps goes through here, and it goes through here. Let's say some of it does go down here, is going to come back up here to this node, right? And so, as we spoke about previously, the 1.5 amp current source is going back on itself, not back on itself, sorry, 1.5 amps is going through the 10 ohm resistor. It's not going anywhere else. And it's going through, and it causes a voltage drop in this direction. And so if there's 15 volts over there, this becomes, let me redraw the circuit so that everybody understands it clearly. It's a good question. Let's say this is the 5 and this is the 20 ohm, right? Let me draw the current source on its side. So you have the current source going here, and I have the 10 ohm resistor in parallel. Okay. This point is A. This point is going to that resistor connection. And this is B. And this resistor is the 5 and 20 ohm resistor in parallel. Okay. The 5 and 20 ohm resistor in parallel, 4 ohm resistor, is connected to terminal B. It's open. No current flows through that terminal. And so the voltage drop at AB is the same voltage drop as across the 10 ohm resistor. And if the current is flowing in this direction, it causes a voltage drop with plus at the top and minus at the bottom. Excellent question. Does it answer?
Yes,
Here, that makes sense. All right, so I'm going to move on. If you have questions, put a pin on it. If you have time at the end of class today, we can answer those. Otherwise, send me an email, come by office tomorrow, and then definitely clear out your concerns and your doubts, okay? All right, so unit superposition, we obtain the same answer. And the mesh current analysis, again, we will obtain the exact same answer because in mesh current analysis, we design a mesh current in two of the meshes. So since we spoke about it, let's go ahead and do it. A, B, 20 ohm, 10 ohm, 5 ohm, 20 volts. Let's assign two mesh currents. We have, let's say, I1 and I2. Okay, I1 and I2. Right off the bat, I can say I2 is equal to 1.5 amps. So the only unknown left for me, or for us, is I1. Write one equation, KVL around M1, and I get minus 20 plus 5 times I1 plus 20 times I1 is equal to 0. Therefore, 25 I1 is equal to 20. Therefore, I1 is equal to 20 over 25. And that gives us 0.8 amps. And if that's 0.8 amps, then voltage across the 20 ohm resistor is 0.8 times 20 gives me 16 volts. On the other side, when I apply KVL, I cannot apply KVL directly because there's a current source, but it's only a single resistor and one single current source. I can simply apply Ohm's law, and I can write V 10 ohms, 1.5 into 10, 15 volts. The end result being the same. V is 15 plus 16. 31 volts. 3 different methods, same answers. And this is something I strongly recommend to all students, is you use all 3 methods to solve for all problems. That would give you, they give you tons of practice and familiarize yourself with all the techniques. Okay. All right, let's move on to Norton current, IN. Now, obviously, we have RTH and we have VTH. Assuming we didn't make an error in RTH or VTH, we can directly apply Ohm's law to determine it, but that would be taking like a shortcut. And so we don't want to do that. We'll find Norton current. We redraw the circuit. And this time we short it out. And now we need to determine ISC. So what do you think? What technique do you want to use? Node voltage, mesh current, or superposition? How would you determine whether to choose between node voltage or mesh current in general? With any suggestions? Well, that's true. But I was just thinking in general terms. When we solve, when we do circuit analysis, what is it we're trying to do? We're trying to solve for unknown quantities, right? Values for unknown quantities. Meaning mathematically, we are writing equations. Equations have variables, unknown variables. And so the lesser number of unknown variables we have, the less equations we have to write. So we count the unknown nodes and we count the unknown meshes in the circuit. Whichever is less is our go-to answer. So in this circuit, we have, let's see, we mark A, B, C, and D, right? Because of the short circuit, A and B are exactly the same. So that takes out one node, right? So now we are effectively left with only 3 nodes. In those 3 nodes, if we choose B as our reference node, then we have an answer for VD. If we have an answer for VD, that takes out one more node, and we are left with only one unknown node, which is VC. So we need only one equation. Once we apply that one equation, we can find the value for VC. Make sense? Right? All right. If we apply mesh current analysis, we can, even in mesh current analysis, we only have one unknown. Because the circuit can be reduced like this. We have a voltage source, 5 ohm resistor, 20 ohm resistor, 10 ohm resistor, and the current source. Technically, all of the bottom node is the same, but this is A, this is B, ISC is flowing in this direction. This is 20 ohms, this is 5 ohms, 20 volts, 10, and 1.5. Let's take a pause while you think over that, redrawing, and let me know if something doesn't make sense. Every time we make a change to the circuit, every time we either short or open anything in a circuit, the circuit changes. Once it changes, you redraw the circuit as many times as you need until it starts to make sense to you. Okay. Because A and B are shorted together, that puts the 10 and 20 ohm resistor in parallel. And because it's in parallel, the circuit looks like this. If it's in parallel, we can reduce that parallel combination to one single resistance. If we reduce it to one single resistance, we are left with only 2 meshes. And in that mesh, we know the answer to one of the mesh currents. Okay. So let's see, it's 347. I'm going to try and see if we can squeeze both node voltage and mesh current in. All right, 20 parallel with 10. Somebody do the calculation. Let me know how much it is. That's 200 divided by 30. Anyone? 200 divided by 30. How much is it? All right, 6.667 ohms. So 20 in parallel to 10. Yeah, 200 divided by 30, 6.667. This is 5. This is 20 volts. This is 1.5 amps. So if we choose mesh current analysis, let's choose a clockwise direction, I1. And this is 1.5 amps. So KVL in mesh 1. Oh, I should have marked this is mesh 1. This is mesh 2. KVL in mesh 1 gives me minus 20 plus 5 times I1 plus 6.667 I1 minus 1.5 equal to 0. So 11.667 I1 minus, not minus, sorry, plus 1.5. So it'd be 5.167 equals 20. Therefore, I1 is 20 minus 5.167 divided by 14.83 divided by 11.667. Therefore, I1 is equal to right, 11.667, 1.2713. 1.2713 amps. Now, we found I1, but that's not the current we want to find. We actually want the current in the middle mesh. So we have to expand it again. Right? We expand it and we write KVL. So actually this turns out to be a bit longer process than node voltage analysis. So if I do that, I have the voltage at 6.667. Yeah, this turned out to be a longer process. Okay. Let's go back up top. And let's do I1, I2, and I3. Okay. It's still possible to solve it using two mesh currents, but now we'd have to apply Ohm's law, find the voltage across both of the resistors, find the currents flowing through the resistors, and apply KCL. Okay, we can still do that, but it's easier to do it this way, I think. I don't know. I've never solved this circuit with mesh current. I've solved it with the superposition and with node voltage, but I've not done it with the mesh current. Okay, so I1, I2, and I3, if we take this second one where we have two mesh currents, we can find the voltage across the 6.667 ohms, meaning across the 20 and the 10 ohms. If we find the voltage drop, we can find the currents through those branches. If we find the current through those branches, we can find ISC by applying KCL at the bottom node. Okay, so I'll leave that for student practice. Let's do the equations for mesh current analysis. Oh, this is poking, it goes out right here. All right. So now I have KVL in M1 minus 20 plus 5 times I1 plus 20 I1 minus I2 is equal to 0. So I have 25 I1 minus 20 I2 is equal to 20. I'll leave that as equation 1. KVL in M2. What do I have? I can write 20 times I2 minus I1 plus, what is 10? 10 I2 minus 1.5 is equal to 0. Right? 20 I2 minus I1. Let me see. So it's going this way. 20 I2 minus I1 plus minus, going this way, plus I2 minus I3, which is 1.5. This is I3. So therefore, I have minus 20 I1 plus 30 I2 is equal to plus 15. Equation 1, equation 2. Equation 1 times 1.5 gives me 25 times 15. I do this manually. 37.5 minus 30 I2 is equal to 30. Call this equation 3. Equation 2 plus 3 gives me 17.5 I1 is equal to 50. Now, wait. 37, 17.5, 0, 45. I1 is 45 divided by 17.5 gives me 2.5714 amps. Plug it into any of the above equations, and you can solve. $20 times 2.5714 plus 30 times I2 is equal to 15. Therefore, I2 is equal to 15 minus, not minus, minus 20 plus into 20, 51.42, 2.5714 into 20, 51.428 divided by 30. Therefore, I2 is 51.428 plus 15 divided by 20. Again, 3.3214. Don't know if this is correct or not. Let's find out. So 31 volts and RTH was what? 14 ohms. So this times 14. Nope, not the right answer. There's an error somewhere in here. I'm going to have to solve it outside of class time. But the process is still valid. There might be an error somewhere in the calculation. Did anybody solve the equations directly? Is mesh current analysis. So there might be an error somewhere. So I2 is the mesh current, and I2 is flowing in this part right there, ISC. So the value that we find for I2 should be ISC, okay, because it's flowing in that mesh. 2.21, direct solving. Okay. Sure, yeah. 2.21 times 14 gives me 30.94. 2.21 is correct. All right. 2.21 is correct. Because 2.21 times my RTH of 14 ohms is approximately equal to 30.94 volts, which our VTH Thevenin voltage is 31 volts. Okay. So the equations we obtained were correct, but my solution at the end was the manual solution I was trying is incorrect. So I just need to look at that. Yeah, and matrix or determinants or Kramer's rule will be faster and easier and less messier. So you tried equations 1 and 2, right? You tried these two? This one. Yeah. Okay, so those equations are correct, that means. All right, great. Just an error. I lost like 5 points, I guess. Okay, any questions? I'll solve it again, but I'll note it down. This was 2.21 amps. And IN times RTH, which was 14 ohms times 2.21, gave us 30.94 volts, which is approximately equal to VTH. All right. Okay, so we'll end class here today. Quiz tomorrow. And if you have any questions about this process, we went fast, but we solved it using multiple different methods. So again, you can Thevenin voltage, Norton current, Thevenin resistance, they're all just applications. It's not a new analysis technique. Always keep that in mind. All right. So we'll end class here today, and we'll see you tomorrow.